Okay, let's get started here. So speaking of epoxide reactions, there is one very important thing that I forgot to cover with those epoxide reactions. So if you noticed, your due date for your epoxide assignment has been kicked back, as well as your end of the week. There's one important thing that we really should have discussed at the beginning, which is the preparation of epoxides. All right, everybody opened up that epoxide assignment and was like, an alkene? What the heck are we supposed to be doing with that thing? And then like MCP, like what is going on here? All right, so we prepare epoxides by starting with alkenes. Okay, and we have two different ways to convert an alkene into an epoxide. So given a normal old alkene with its carbon-carbon double bond, there's two different ways of doing it, and there's some pros and cons to each. Kind of the cheap way, but if you try to do it in practice, it's kind of a pain in the butt, is to use bromine and water, and then in a separate step, follow that up with some base. I don't remember what, some hydroxide. Potassium hydroxide, sodium hydroxide, doesn't matter. Some base. I don't remember what's in the homework. All right. And what this will do is replace that double bond with an epoxide. Remember, an epoxide is necessarily that three-membered ring ether. All right, so the two carbons that are in that three-membered ring are those alkene carbons, that carbon-carbon double bond. All right, another way that you can do this, that's a little bit more expensive, but it works a little bit better, is using what's called a peroxy acid. And there's one particular one that they like to use, MCP-BA. All right, and that gives you the exact same thing, okay? So importantly, whether you choose to do the cheap and easy method or the more expensive fancy method, you get the exact same epoxide products, all right? There's no difference between these two methods in that respect. All right, so let's just note, same epoxide regardless of your synthesis method. Or regardless of reagents, I guess we should say. Okay. All right, so then for the sake of practice, let's try doing one kind of as we see it in our homework here. Starting out with a alkene, and then we have in the first step the MCP-BA, and then in the second step we need that nucleophile. We'll do this negatively charged sulfur here. I lied. Let me change up this alkene. Hiya. We're going to put an extra methyl group on there. Okay, so that first step is just creating that epoxide. To be clear, these two carbons that I colored in red here about my double bond. When I go to draw my epoxide, that's where my triangle is going to be. Those two red carbons plus, we got our oxygen here. All right, and so now we got to do step 2, which is to treat it with this nucleophile. All right, and so now we got to do this law. This part we did learn last class. All right, we got to look at this nucleophile right here, and we got to ask ourselves, is this an acidic conditions nucleophile or a basic conditions nucleophile? Let's take a poll. Who thinks it's acidic? Raise your hand. Who thinks it's basic? Raise your hand. Okay, cool. What makes it basic? That negative charge, right? So this would be a basic conditions nucleophile. All right, and under basic conditions, primaries are preferred over secondaries, are preferred over tertiaries. All right, so I'm going to sort of change my carbons coloring here. Let's make them two different colors. Okay, I got to say, all right, this red carbon would be considered what? Primary, secondary, or tertiary? How many carbon neighbors does it have? 2. It's got this one and this one, so this would be a secondary carbon. And what about my green carbon? How many carbon neighbors? 3. And since under basic conditions, it's all about what's more accessible, my secondary carbon is what's preferred. That means that I'm going to attach that sulfur, attach that nucleophile to that secondary carbon. Okay. So I'll keep my coloring here. I'm going to have now that nucleophile on my secondary carbon. And what needs to go on that other carbon? The OH, right? Your nucleophile gets added exactly 1-2 carbons away from that OH. Well, all right, so we kind of glossed over this first step here, which is probably the most important part. How do we get our epoxides in the first place? We start out with alkenes, right? Alkenes are a great starting point for synthesis. There are a lot of different reactions we can do. And in particular, we can make an epoxide using one of these two methods. In terms of the epoxide you get, they're exactly identical. All right, bromine and water followed by some base. That'll turn an alkene into an epoxide. Or that fancy MCPBA will turn an alkene into an epoxide. Right? In either cases, your 3-membered ring, the 2 carbons, are the 2 carbons that were about that double bond. Right? So after that first step, after we create our epoxide, we're going to treat it with some sort of a nucleophile, and we got to go through that process we talked about last time. We got to first categorize our nucleophile as being acidic conditions or basic conditions, because that'll help us determine which carbon is going to be substituted in our product, or added to, I guess, more specifically, in our product. Cool? All right, so new week, we got a new functional group here. All right, and we've talked about these a little bit, but now we're going to kind of more formally introduce them. Our discussion for this week is going to be aldehydes and ketones. All right, so let's just draw an example of each. All right, one of these is an aldehyde, one of these is a ketone. I want you to see if you can remember which one's which here. Which one's which? What's on the left? The aldehyde. Okay, so aldehydes always have those carbonyl groups on the end. So they always have this same basic formula, R connected to that carbonyl group. Both of these are carbonyl compounds. So RC, going to draw that carbonyl group. But then since that carbonyl group is on the end, it's necessarily bound to a hydrogen, right? There's this implied hydrogen over here on our aldehyde because it's on that terminal carbon. Okay? So aldehydes are terminal carbonyl groups. Ketones also have those carbonyl carbons, but they're sandwiched between two other carbons. So those would be internal carbonyl groups. All right, but we always study aldehydes and ketones together. Aldehydes and ketones both undergo the same types of reactions. All right, so then why do we distinguish between them at all? Kind of the bane of my existence as a chemistry instructor. We should just lump them into the same category. Historically, these are separated into these two different categories because some of the earliest work that was done in organic chemistry revolved around sugars, and it turns out that all the sugars in the world fall into one of these two bins here. So that was kind of an easily distinguishable things about sugars early on, where we put them into these two bins. They called them aldoses and ketoses, and now all of a sudden that kind of different categories have stuck. Okay? But in terms of our minds, we're going to lump them together because they behave the same in terms of the chemical reactions that they undergo. All right, and we've talked a little bit about this before. Let's call this our structural features. All right, we've seen aldehyde, even though they haven't really been like the topic of our chapter before, we've seen them both as reactants and products, specifically in that alcohols reaction, alcohols chapter. All right, and what we're going to see over and over again is our aldehydes and ketones playing a very specific role in chemical reactions. All right, and it has everything to do with this very polar bond right here between my electronegative oxygen atom and this carbon atom right here. Right, oxygen being so much more electronegative is able to pull a bunch of electron density onto itself, giving it a partial negative charge. All right, and since it's stealing that electron density away from that carbon, that leaves that carbonyl carbon with this partial positive charge. All right, and so because of that, our carbonyl carbons are good electrophiles. They're left relatively electron deficient. They got this partial positive charge, so they'll accept negatively charged electrons. All right, so our carbonyl carbons are good electrophiles. All right, and so reason number one is what we just illustrated here. They are electron deficient because of that polar bond. All right, but there's something else that makes those carbonyl carbons really good electrophiles. I mean, not every carbon in a polar bond is necessarily an electrophile, okay? The other thing that makes these so good, right? Remember, electrophiles, they have to accept pairs of electrons. All right, so why can this carbon atom accept a pair of electrons really well from some nucleophile? All right, well, when that nucleophile attacks that carbonyl carbon, all right, if we just stop there, carbon would have too many electrons, right? We'd be breaking carbon's octet rule. So the other reason why this carbon is so good at accepting electrons is because it can break this pi bond, and that oxygen, being so electronegative, is more than happy to accept those pair of electrons. All right, so these reactions undergo this intermediate here. Where we have our nucleophile attached, and we have this oxygen that has a negative charge. All right, and so this is going to be an intermediate. We call this a tetrahedral intermediate. But importantly, nobody's had to break their octet in the course of this reaction, right? So everybody remains relatively happy from an energetic standpoint. Carbon didn't have to break its octet in order to accept that pair of electrons. Okay, so carbonyl carbons are good electrophiles because they're electron deficient, but they can also accept pairs of electrons without breaking their octet. All right, so we need both of these things together to understand why carbonyl carbons are such good electrophiles. They're relatively electron deficient because of that polar bond, but they can also accept pairs of electrons and never break their octet. Okay. All right, one of the other things that we've been doing is we've been sort of ranking our functional groups based on polarity. And this is sort of to help us understand how these compounds are used in the lab as solvents, right? So we sort of broke from our traditional general chemistry way of looking at things as being either black and white, polar or nonpolar. And we started thinking about things as being on this spectrum. On the one side, all the way nonpolar. And on the other side, we have our very polar functional groups, right? We've kind of been filling in this spectrum with these various functional groups. All right, the most polar solvent that you can get is water. All right, what about the most nonpolar solvent? What do we use if we just want like a strictly super duper nonpolar solvent? What functional groups? Alkanes, yeah, just carbons and hydrogens. All right, so these are kind of our two extreme ends here. As another polar functional group, not quite as polar as water, because we got some carbohydrates, hydrocarbons, there it is, geez. Some hydrocarbons on there would be alcohols, but still pretty far on that polar end of our spectrum. Okay. Last week we talked about ethers. Where do they fall on this spectrum? The polar end or the nonpolar end? All right, with an ether now you don't have that OH group. You can't do any more hydrogen bonding. They got some electrons, so they're a little bit more polar than our alkanes, but not much. They're pretty far down here on the nonpolar end of our spectrum. Okay, so then we have now our ketones or aldehydes. This particular is a ketone, but again, we're going to lump them together. Let's just say or aldehydes. Okay, so this thing right here has this polar bond between carbon and oxygen, right? But it's not quite as polar as an OH bond. It can't undergo that hydrogen bonding. So ketones and aldehydes are kind of sitting pretty much in the middle, maybe a little bit more over towards the polar end of the spectrum here, all right? But not quite as polar as your alcohols. All right, this makes them really convenient to use, especially for washing glassware. The most common use that you will find in an organic chemistry lab for a ketone is to wash glassware because it mixes with water, but it also mixes with all the nonpolar crap that's going to stick to your glassware, right? So it's kind of great right in the middle of these two ends of our spectrum where it will dissolve polar stuff, but also relatively nonpolar things as well. Cool. All right. So, as always, we get to start with everybody's favorite place here, nomenclature. And this is really the biggest difference between these two functional groups because they have the exact same reactions, but we name them differently. So we're going to break them up. Nomenclature of aldehydes. We'll start here. All right, and let's actually do an alcohol real quick. So you can kind of compare here. Same number of carbons, but we'll make this an OH. All right, everybody take a second and name this alcohol for me based on what we discussed last chapter, and then we'll kind of extend that to this aldehyde below. So this would be 1-bute. What ending do we use for alcohols? OL. All right, but remember we also keep this AN in here. So it's not just butol, but butanol. And what is that AN in there telling me? All single bonds, right? And we kind of didn't get any more complicated than that, but if we did have like a double bond in there, that would change to an EN, or a triple bond, a YN, but we're not going to complicate things in this course. But that's why we retain that AN in there to indicate that there are only carbon-carbon single bonds here. All right, that's going to be important. We'll see something similar with our aldehydes. Nomenclature, we're going to have these same steps that we always have, where we're going to find our parent chain. All right, that's our longest continuous set of carbons that contains that functional group. All right, last week we were talking about nomenclature of ethers, and ethers were kind of weird because in our nomenclature they're not considered functional groups, all right? we're kind of back to regularly scheduled programming here where aldehydes and ketones are considered functional groups. You'll sort of add a different suffix onto the end of the name. All right, and so we can just make note here for aldehydes. That suffix is not OL like it is for alcohols, but AL for aldehydes. All right, we can leave a little room here. We'll sort of put our ketone rules in this as well. We'll have a different ending for ketones. Okay, 2, we got to find and name our substituents. There's nothing new to add here. We don't have anything fancy going on here. And 3, now we got to number that parent chain. All right, we're going to add some rules here. So I'm just going to leave some space and then say assemble our name, nothing different there. All right, so let's see if we can apply these rules to our aldehyde here. We said it was 1 butanol above. We're going to find our parent chain. How many carbons are in our parent chain? We got these same 1, 2, 3, 4. Okay. So using our new suffix, this is not butanol, but butanal. All right, that's my parent chain here. My 4 carbons plus my 4 carbons, all single bonds, aldehyde functional group. Okay. All right, I got to number this parent chain. So where am I going to start carbon 1 at? The left or the right? Right. And why the right? We want the lowest number on that functional group, right? So 1, 2, 3, 4. Okay. Cool. So if I pick this thing up and moved it over here to the other end, how would that change my numbering? I would just start numbering in the other direction, right? Because again, we want the lowest number in the name. What if I picked this thing up and moved it into the middle here? Now I don't have an aldehyde anymore, right? So an aldehyde is necessarily going to be on that end carbon. And since that's where we start numbering, we're always going to put that aldehyde functional group on carbon 1. So because of that, we don't have to say that this is 1 butanol. There is no such thing as 2 butanol, 3 butanol, 4 butanol. There's no other possibility but to put that carbonyl group on carbon 1. So for aldehydes, we've kind of seen this before, and we'll see it again with aldehydes here. For aldehydes, we do not have to include the locant in the name. Do not include locant. All right, so this thing here isn't 1 butanol, but just butanol. All right, again, aldehydes, it's not going to be, there's no sort of ambiguity as to where you put that carbonyl group. You're always putting it on carbon 1. Okay. And let's just do another example underneath it, but this time we'll do a ketone. Okay, So the first step is going to be to distinguish, am I looking at an aldehyde, am I looking at a ketone, right? So we want to be able to spy that this is indeed a ketone. For ketones, we're going to use a different ending. Aldehydes are al, ketones are -one. All right, so let's go through our rules here. How many carbons are in our parent chain? 5. All right, we're going to number our parent chain. 1, 2, 3, 4, 5. If I went the other way, it would be the same here. So my parent chain here is pent, -one. Okay, we got a similar breakdown to what we saw before. The pent is telling me what?
5 carbons.
That I got those 5 carbons. The an, all single bonds. I guess to be clear, all carbon-carbon single bonds. Obviously I have that carbon-oxygen double bond. But this is telling me I have all carbon-carbon single bonds. And then that -one ending is because of that ketone functional group. Okay. Cool, and we numbered this parent chain here. We see that this ketone group, this carbonyl group, is on carbon 3. Do I have to include that in the name? All right, if I picked this carbonyl group up and moved it, would this also be a ketone? Yes, and it would be a different ketone, different physical properties, all that sort of jazz, right? This would be 2-pentanone. I need to indicate that I'm talking about a specific ketone here. This would be 3-pentanone here, right? So for aldehydes, we do not have to include the locant. For ketones, we do include the locant in the name. Okay, so aldehydes and ketones, we're going to have different suffixes, different endings for these different functional groups. Aldehydes have that suffix al, ketones have that suffix one. All right. Besides that, the only difference is that when we're doing our numbering for our parent chain, for aldehydes, they're always going to be located on carbon 1, so we don't have to include that 1 in the name. But ketones are going to be anywhere in the middle of the molecule, so we do have to include our locant in the name. All right, so let's just do some examples. I'm going to put down some molecules, and you're going to name them for me. let's do this. All right, so I'm going to find that parent chain, 1, 2, 3, 4, 5 carbons long. Is this an aldehyde or a ketone? Aldehyde, so I don't even have to worry about my numbering. It's always going to be on carbon 1, so this would be pentanal. All right, my other example here. My parent chain is 1, 2, 3, 4, 5, 6 carbons. Is this a ketone or an aldehyde? Ketone. So now I do have to worry about my numbering, right? So I'm going to put in that numbering scheme to give that carbonyl group the lowest number. So this would be 2-hexanone. Okay. How many carbons are in my parent chain on this next example? 6. I got my 1, 2, 3, 4, 5, 6, and I know it's got to include that carbonyl carbon because it has to include that functional group. All right, so then what the heck are these 2 carbons over here? An ethyl group. All right, we're going to number our parent chain, but I automatically know what carbon is carbon 1. That carbonyl carbon. Okay, so I need to put that substituent out front. This is a 3-ethyl, and then I don't have to include the 1, so 3-ethyl hexanal. All right, and then lastly, we have these 1, 2, 3, 4, 5 carbons in my parent chain. I'm going to number my parent chain both directions here. All right, and which one of these numbering schemes is correct, red or blue? Red, right? Because we're going to prioritize our functional group. So I don't care about that chloro group. I only want my carbonyl to have the lowest possible number. I guess we can just note this would be a chloro group. All right, when I put my name together, we always put those substituents out front. So this would be 4-chloro-2-pentanone. Cool, so here are our nomenclature examples here. All right, our aldehydes have that Al suffix, and our ketones have that ONE suffix. We always got to include the location of substituents, but we'll note that in our aldehyde, we don't indicate that that Al is on carbon 1, but for ketones, we do indicate the position of that carbonyl group. All right. Lastly, there are 2 special aldehydes and ketones that we got to know. I guess one of each. All right. These are aldehydes and ketones that, you could give them an IUPAC name, but nobody calls them that. Nobody would have any idea what you're talking about. They have their own kind of special name. All right, and it's actually our smallest aldehyde that you can have. All right, where that carbonyl carbon is bound to not 1 but 2 hydrogens. Or our smallest ketone that you can have, where there's just 1 carbon on either side of that carbonyl carbon. All right, so again, this thing right here, if we used our IUPAC system, this would be methanal, but nobody calls this methanal. Does anybody know what this is by chance? If you were in biology and particularly in the dissecting of animals business, Formaldehyde, all right? And this is that molecule right here. So methanal, nobody calls it methanal. It existed for way too long and was way too popular already and already had this name formaldehyde. So the IUPAC was like, screw it, we'll just keep on calling it formaldehyde. All right, and yes, if you've ever taken a biology class where you dissect anything, it's got this particular aroma to it, and that is formaldehyde, so preserving agent.
You have to get, the burial home has to put formaldehyde in you even if you're going through cremation.
Why?
I guess like it might take days to.
Oh, okay, fair.
That's
just big formaldehyde right there,
yeah,
getting you to spend money. All right, and then this one right here also has its own common name. You could call it propanone, but nobody calls it propanone. Does anybody know what this one is? If you, it's the active ingredient in most nail polish remover. Acetone. All right, so these are both aldehydes and ketones, but they do not go by their IUPAC name. They go by these special common names here. We have the smallest aldehyde that you can have, formaldehyde, with just one carbon, or the smallest ketone, acetone. And so these are the names of these molecules. We just got to know that. Okay. Cool. All right, so let's remind ourselves real quick. We've seen aldehydes and ketones before as reactants when we were creating alcohols. Let's just kind of review it here because what we're going to see is a similar pattern over and over and over again throughout the course of this chapter. All right, so these were what we called Grignard reactions. Okay, so Grignard reactions, the whole shtick of these was that Grignard reagent is a good carbon nucleophile. Right? Specifically, that carbon bound to that metal has a ton of electron density. And so this is going to be our nucleophile in our reaction. And what's our electrophile? Yeah, right? Remember at the very beginning, what did we say about the structural features of aldehydes and ketones? Our carbonyl carbons are good electrophiles. All right? You want to have that phrase kind of burned into your mind, electrophilic carbonyl carbon, because that's what we're going to see over and over and over again. All right? This thing right here, we have our electrophilic carbonyl carbon. All right, and in this reaction, we're going to have our nucleophile doing what nucleophiles do and attacking electrophiles. All right, so we're going to get this new carbon-carbon bond. I'm going to start by redrawing that nucleophile. All right, I draw my 4 carbons. Now I get to that blue one. So when I draw this new bond over here, what's on the other end has to be that red carbon. All right, that's my Grignard being added on here. All right, my Grignard also has these other 2 carbons. All right, so we have this new carbon-carbon bond. All right, and what we're going to see is this is super common. It's not always a carbon-carbon bond, so we're going to say it's a new carbon nucleophile bond. because that's going to be true for all of these reactions of aldehydes and ketones that we study. All right, specifically that carbonyl carbon is going to have some new nucleophile attached to it. All right, there's something else that I'm missing from this reaction here. We studied it in the alcohols chapter for a reason, right? And that's because I have this alcohol product. I don't actually lose my carbonyl oxygen. It just goes from being a carbon-oxygen double bond to a carbon-oxygen single bond. Okay? And this is what we're going to see over and over and over again for this particular chapter. We have this new carbon nucleophile bond, and our carbonyl oxygen becomes a alcohol oxygen, or a hydroxyl oxygen. All right, so this is this Grignard reaction that we studied. This is a subset of a much larger class of reactions of aldehydes and ketones, what are called nucleophilic addition reactions, where we're adding some nucleophile specifically to that electrophilic carbonyl carbon. All right, so we have these nucleophilic addition reactions. All right, and so we're just going to kind of do our generic form here. We have our nucleophilic, our electrophilic carbonyl carbon. All right, I'm going to add in some nucleophile here, some negatively charged nucleophile. And I want everybody to take a second and see if you can't give me the product of this reaction using my little variable Nu nucleophile. Right, so I have my 4 carbons from my electrophile, and when I draw my new bond, what's on the other side of that new bond is that nucleophile. All right, and what else do I need to draw on that blue carbon? That OH group. Okay, that's my oxygen from that carbonyl. Now it's got this hydrogen on there as well. Okay, just to be clear, you're kind of like, well, where did that hydrogen come from in the grand scheme of things? This is usually from your solvent, right? So there's just hydrogens floating around. You either do this in an alcohol or in water or something like that. And so there's going to be these hydrogens that you can take from your solvent. Since we added it, just like all of our negatively charged nucleophiles, when we add them, they lose their negative charge. It's actually this pair of electrons right here that forms that new carbon nucleophile bond. All right, so let's remember, just in our previous chapter, we talked a bunch about nucleophilic addition reactions. Okay? And we broke the world up into basic nucleophiles. And what did our basic nucleophiles all have in common? Negative. They had that negative charge. And then we had acidic nucleophiles. What do our acidic nucleophiles have in common? They're all neutral with the exception of these halide ions here, which are negatively charged, but where they're allowed to be in acidic conditions such that because they're such crappy bases, right? So we are going to see these same nucleophiles again, all right? Fortunately for aldehyde and ketone reactions, we don't really have to pay attention to whether they're acidic or basic. We get the same product regardless of what conditions you use. Truthfully, in a little bit more of an advanced course, you'd do mechanisms, and your mechanism would depend on conditions, but for our purposes, we don't really care, all right? So we're going to see these same things over and over again, these same nucleophiles over and over again, but we don't really care about the acidic and basic category like we used to, okay? The one thing we do have to remember about our neutral nucleophiles is what do we have to do when we add our neutral nucleophiles, just like we did with epoxides? They're going to lose a hydrogen, all right? So we got that same thing that we got to consider, but nothing too crazy, all right? So let's see if we can't just sort of by analogy here and what we've discussed, take a few real examples. All right, we'll do butanal. And let's do a ketone. All right, so what's my electrophile here? The electrophilic carbonyl carbon. All right, so my electrophile is always going to be that carbonyl carbon. In this molecule here, SH, which one of these atoms is my nucleophilic site? The sulfur that's got all that electron density, right? So that's going to be my new bond between my nucleophile and my electrophile. Do I have to take a hydrogen off of it? No, because it's negatively charged. It'll just be neutral when it gets added. And then I'm done. I got to add that OH as well. All right, that oxygen is going to become a hydroxyl group. All right, I got my ketone here, so that electrophilic carbonyl carbon. And what atom is my nucleophilic site in my nucleophile here? The oxygen or the hydrogen? The oxygen. Again, we need all that electron density for it to be a nucleophile. All right, so I'm going to redraw my electrophile here. I'm going to add that new bond to my nucleophilic oxygen. And how many hydrogens should I have? Just one. I need to get rid of one since this is a neutral nucleophile. All right, and then I'm done. I still got one more OH group on that exact same carbon here. All right, importantly, where did that second oxygen come from? Well, that was already on there. That was my carbonyl oxygen. All right, so now we have two hydroxyl groups on that same formerly carbonyl carbon. One came from my nucleophile. That's how one got added. And one of them was already there, my carbonyl oxygen. All right, fun fact, these have a name here. These are called Chem8FA24, which I really didn't get at first, but I guess that prefix gem, like Gemini, has something to do with twins. I don't know, I'm not a word person. But yes, anyway, these things have a special name, Chem8FA24, because you got these twin alcohol groups on that same carbon. Okay, cool. So we're going to add that nucleophile to that electrophilic carbonyl carbon. So in each of these, we have that new nucleophile carbon bond. And we have our carbonyl oxygen becoming an OH group. Okay. One more thing that we're going to do is we're going to stack two examples next to each other from this chapter and from the last chapter. All right. What do I mean by that? So let's do this ketone, but then let's also do an epoxide we're going to react these with our same nucleophile. Okay, and I want everybody to take a second and give me the product of these two reactions here. let's take these one by one at first, and then we'll kind of stack them next to each other and compare. All right, so my electrophile is going to be that carbonyl carbon. My nucleophilic site will be that sulfur with all of its electron density. So when I go to draw my products, I'm going to draw that new bond between that electrophilic carbon and that nucleophilic sulfur. All right, and then I got to include those other two from my nucleophile. All right, and then lastly, what am I missing? That carbonyl oxygen, still attached to what was formerly my carbonyl carbon. So I have this OH group here. Cool, we got our nucleophile attached to this formerly carbonyl carbon that still has that oxygen bound to it. All right, let's do our epoxide reactions. These epoxide reactions, way more of a pain in the butt actually. I got these two carbons. All right, which one is going to be attacked by my nucleophile here, green or blue? Green, because it's a basic nucleophile, and that green one is more accessible. Okay. So I'm going to redraw my electrophile here. Now I have to have my new carbon nucleophile bond. All right, and what else am I missing? That OH, that epoxide oxygen is still there, but importantly, which one am I going to draw that hydroxyl group on? Blue or green? Blue. It's going to be on the other side because of that ring opening reaction. All right, so let's take these two examples and stack them next to each other here. Kind of finish my color coding. All right, importantly, what's the same about these two reactions? If I look at my product, I got the same two functional groups in there. They both give me a nucleophile added on and a hydroxyl group. Right? So we could just note here, both reactions have our nucleophile and an OH in our products. All right, but what's the big difference between these two reactions? The spacing. Exactly. So look, if we look on our first reaction here, that nucleophile and that OH group are on the exact same carbon. If we look at our epoxide reactions, remember what was the signature of those epoxide reactions? Is your nucleophile is always added 1, 2 carbons away from that hydroxyl group, right? If I picked this thing up and moved it over, I'd have the exact same product, right? But in our epoxide reactions, that nucleophile gets added 1 carbon away. All right, so let's just make a note here. For our aldehydes and ketones, these are on the same carbon, right? That formerly carbonyl carbon. And for our epoxide reactions, all right, they are located 2 carbons away. All right, we have a very similar type of reaction, another nucleophilic addition reaction, but where exactly that nucleophile is being added relative to that hydroxyl group is the big difference between these two products here. Cool. All right, we'll finish this up next time.